So let's just define it for positive integers today. Positive integer k is prime if k is greater than 1 and the only positive divisors of k are 1 and itself. So we do not allow 1 to be prime for reasons that we will talk about later. But for now, you can just know that 1 is not prime. What I want to show you is what's called the Sieve of Eratosthenes. Eratosthenes was a mathematician. He looked at how to generate all prime numbers up to a certain number. So let's say I want to generate all the numbers up to 50. I'm going to write out the numbers up to 50, out 1, and then circle the first uncrossed out number. So the second step is to circle the first uncrossed number and then cross out every number that is that far apart. I'm going to circle 2 because it's the first not crossed out number. And now I'm going to cross out every second number. So 4, 6. So I come back, the first uncrossed out number is 3. So I'm going to come to 5, and 5 is not crossed out, so I circle it. So I'm going to cross out every fifth number. I come to 7. 7's the first uncrossed number, so now I'm going to cross out every seventh number. And I come to 11. 11 is not crossed out, so I circle it. Then I cross out every 11th number. I come to 13. 13's not crossed out, so I cross out every 13th number. I come to 17 is not crossed out. I cross out every 17th number. 19 not crossed out, and I just keep doing this. And then I get to, now I'm in the place where none of the next steps would be in the numbers. So here are the numbers that are prime that are less than 50. And here is a procedure that helps me find them all. This was known to the ancient Greeks, and it was called the Sieve of Eratosthenes. Why did I talk about algorithms on a day that we also talked about theorems and proofs? Well, it turns out that they're actually very closely related. So there's something called the Curry-Howard isomorphism, or the Curry-Howard correspondence, which says that every computer program can be written as a mathematical proof and vice versa. But now computers are useful tools in the proving game. For the types of proofs that we're going to be doing proofs that we can approach by hand. A computer program can be rewritten as a mathematical proof, and a mathematical proof can be rewritten as a computer program. And you can check that they're equivalent. Proving that a program is correct is something that people do. Writing a formal mathematical proof that a program will do exactly what you want it to do is something that people do in certain situations when the stakes are very high. If your program is not that important, you don't need to worry about it. The people who write programs for the military or for banks, where the computer chip manufacturers will have the correctness of their logic on their circuits actually formally proven. And that way you know with 100% certainty that what you are doing will work. So what I like about mathematical proof is it eliminates this sort of nagging uncertainty that we often feel about the world. When you prove something, you know that it is true, at least as a mathematical statement. And that's a tremendous sense of certainty and security.